So in conclusion, I would like to present to you the Misty report. The Misty is a programming language which represents the next paradigm, the next major advance in programming languages. And I've been working on it for about 50 years or so. And over the years, as I've continued to get hopefully smarter about my profession and how it all works, I've very much changed my idea about how to go forward with the next paradigm. And every decade or so, I changed the working name of the language. It started as Crockford. Maybe the best name was Elemento. That's a really good name. But then it became Neo, and now I'm going to talk about the version which is called Misty. So 50 years seems like a really long time to be working on a programming language. It's like I'm not making significant progress, am I? Particularly, it's not done yet. And the reason I call it Misty is because it is literally vaporware. It does not exist. There's no promise that it will ever exist. But I think it's really good. And so I'm sharing it with you today. So despite the fact that I have nothing to show, I actually have a few things to show. As a consequence of working on Misty, I have developed some other things, a few of which have become important, like JSLint, the rediscovery of top-down operator precedence, which is an idea developed by Von Pratt, a brilliant guy out of Stanford. It is a brilliant way to do parsing, a very easy way to implement programming languages. JSON, you've heard of JSON. I heard it mentioned earlier this morning. Parsec, which is a very good way of dealing with asynchronicity. And the SAFE protocol, which was developed at PayPal, which provides a better, secure platform for doing distributed programming. And a couple of books, JavaScript, the Good Parts, and How JavaScript Works. So making programming languages is a great hobby, particularly if you're a programmer. It gives you insights into the most important tool that you have for doing your work. And the better you understand that tool, the better your work can be. So programming languages are easy to make, especially now we've got very good things like top-down operator precedence for doing parsing. We've got LLVM for code generation, or you can transpile into JavaScript or other languages. It's never been easier to make a programming language. Although most new programming languages offer little real value over their predecessors. Most of them tend to be pretty much another language with slightly different syntax or a new feature or two. It requires extraordinary luck to get adoption. Most new programming languages, no one ever hears of them, even if they get finished. And it turns out that you don't necessarily need to be a good programming language in order to get adoption. And in fact, there are lots of examples of really awful programming languages which have become the standards and we're continuing to be stuck with. So a clever programmer can make a new language. It takes an army of coders to maintain it, to create all the different versions and updating, creating standards, all of that stuff. You know, one guy made the C language. Brilliant guy, Dennis Ritchie. And who knows how many people have gone after him maintaining that awful language. Some languages don't become popular except with language designers. So these are languages which you don't see in the mainstream, never really did. But people who design languages deeply respect those languages and try to implement them or are influenced by them. So the next language should try to do something useful. It should try to promote a new paradigm which allows better solutions to our current problems. So being a maker of programming languages can make you a better critic of programming languages. So if you're designing these things yourselves, when you're confronted with a new one, you have a better place to stand for evaluating it and deciding, is it good and how should it be used? So I've done a lot of work with JavaScript. JavaScript has some really good parts, amazingly good parts, which I think make it the most important language in the world today. It has flexible objects. It has first-class objects with lexical closure, which is the best idea in the history of programming languages. JavaScript was the first mainstream language to do that. It's also called Lambda. And it's optimized for event handling. If you're doing stuff in the browser or even in Node, everything is, the program just sits there until an event happens and then it starts to run. That turns out to be the right way to do things. For a lot of people working in other languages, it seems completely alien, but this is the way forward. Now, JavaScript is also burdened with a lot of bad parts, which includes everything else that's in the language, including most of the new parts. TC39 at ECMA keeps adding new bad parts to the language. They just can't stop. One of the most recent bad parts is the sequential illusion confusion, which you see in promises and async await for dealing with asynchronicity, but they're awful. Promises were invented at a company that I founded called Electric Communities, and eventually they found their way into JavaScript. But I now consider that to be a mistake. I'm sorry. These things happen. And then async await is much, much worse. The thing it promises is that you can take an event-driven asynchronous program and make it look exactly like a synchronous program. But that's not what it's doing. So if you write a program that looks different than what it actually does, it's very easy to be confused about what the program is doing. And if you don't understand what your program is doing, there's a really good chance it's doing something wrong. So JavaScript should not be the last programming language. You know, for the kids, right? You want their legacy to be better than JavaScript. This isn't where it ends. We have to go past this. We have to figure out what comes next. And I've been devoting a lot of time to that problem. What happens after JavaScript? So here's an example of what goes wrong. This is a fairly new part in JavaScript. I call it the WTF operator. It replaces the dot operator. The dot operator is obviously the thing that you use to create a path into an object. You know, if you have an object of objects or deeper, and you want to find a property inside of this deep thing, you go name.name.name, and then you get it, except the dot operator was defined incorrectly, so that if anything is null or undefined, it blows up rather than return undefined, which is what should happen. This operator works correctly, but it's so appallingly ugly. So this is the one you should use. You should not be using dot anymore. You should only be using this abomination. But I look at a program that has a lot of these in it, and I go, what the? It's just so ugly. That it can't stop here, right? We have to go on. So looking to think about the next paradigm, we can first look at the paradigms we've already gone through. And this is my opinion as to the important paradigms in programming so far. The first, we start with the von Neumann machine. And most of our computers are still based on the von Neumann architecture, at least to some extent. And the first generation of von Neumann programmers were coding in binary, which was really hard. So the next generation was, let's do that symbolically, that we now know that as assembly language. That was a big step forward. But at the time, it was a controversial thing, because at the time, computers were extremely expensive machines, and human life was cheap. So management thought we should not be wasting computer time on things that humans can be doing. But that turned out to be wrong, and there were some brilliant women like Grace Murray Hopper who actually led the way to using computers to make it easier to write programs. The next step was high-level languages, one of the first of which was Fortran. Next was structured programming, which really starts with Algol but gets to the mainstream with C and Pascal. Then object-oriented programming, which was inspired by Simula, which was developed in Norway. It was an Algol variant. Alan Kay invented Smalltalk, which is the best designed programming language in history, but we didn't go with that, right? We went with C++ instead, which is really awful. And different people who deal with object-oriented programming have different opinions as to what is or isn't object-oriented. For example, there are some people in the C++ community who say that JavaScript is not object-oriented, even though it is. Although there are people in the Smalltalk community who will say C++ isn't really object-oriented, and they are probably right. And then the most recent one is functional programming. We've had this for a while in languages like Scheme and Haskell, but it reaches the mainstream with JavaScript. One of the amazing unknown things about JavaScript was that it is a really good functional programming language, and that is an important paradigm, and that's what we should be doing now. But the thing that all of these paradigms have in common is a model in which a program runs in a single machine. And that is not the world we live in today. In our world, we have many processes per machine, not just one, and those processes may be interacting with each other. We have many machines which are interconnected, and a program can be distributed over many machines. Our current programming languages don't understand that concept at all. Machines are now very fast, although the old paradigms were all designed for a time when machines were very slow. And so the trade-offs they made in the design of the languages were to mitigate that, but in doing so, they gave up opportunities to do better things. Machines today have very large memories. That didn't always used to be the case. C was designed for a target machine with 16 kilobytes, which is unimaginably small in our current context. But that was the whole machine, and they wanted to run, and so they crafted a programming model that could fit in that tiny programming space. C++ just copied that, and we're kind of stuck with that. We should be thinking differently about how things work, but we still have our programming languages telling us to think in a very small memory model. Reliability requirements are getting increasingly strict as more of what the world does gets put into software. And insecurity is our biggest problem. When we have all these machines that are interacting, that creates enormous opportunities for terrible things to happen. So we need a programming model that fits our distributed world. Up until this point, we've just been slapping new features onto the old paradigm, but I think the best way forward is to imagine a programming model that works with the new paradigm. And I think that model is the actor model. The actor model was discovered at MIT in the early 70s, around 72 or 73. And it is just now starting to get some attention. It might seem odd, why did it take so long? And maybe we'll talk about that later. But this is actually the way forward. So the thing I like about the actor model is that the concurrency model, or the asynchronous model, the communication model, and the security model all come from a single mechanism, which is message passing. Everything happens with message passing. There is no sharing of anything. The errors and security blunders that can happen by sharing are impossible. They're just factored out. It's so elegant and so clean and simple. And if you're dealing with something as complicated as distributed systems and security, you want to start with the simplest thing. And I think this is it. So I'm going to give you my opinion as to what an actor model is. And as with object-oriented systems, everybody who is inventing something with actors has a different opinion as to what actors are. And reasonable people can disagree. But it turns out that I'm right. So for this presentation, just assume that everything I'm about to tell you is the right way to think about actors. So an actor, and they'll all agree with most of this because the others are mostly right. So an actor is a program running in a single process in a machine. An actor communicates with other actors by message passing, and that is the only way that it can communicate, the only way that it can share information. There is no sharing between actors, even on the same machine. An actor can create new actors in its own machine, but not in others. Every actor has a private address. And if you have an actor's private address, you can send messages to that actor. If you do not know the actor's address, you cannot send it messages. That is the fundamental thing that gives us security. And messages can contain private addresses. So an actor can put an address into a message and send it to an actor. And that actor can now communicate with the thing that it was sent. Actors can have state, which can change based on received messages. Incoming messages are queued if necessary and delivered in arrival order. If you do event programming, this is very, very familiar. Actors run when they receive messages. Again, this is very familiar. That's how event handling works. An actor will not be given another message until it is done. Again, messages sent by an actor will be held until it's done. So you have a turn, and in that turn you can do some processing and send messages, but the messages won't be sent until you successfully complete the turn. An actor's turn can be time sliced. So this is something that we can't do currently in JavaScript. So if you have an actor that needs to do some computation and it's going to do a long time, it's just going to sit there grinding, that's fine. We can time slice it and let it go as long as it needs to go. You can't do that in the web because you're holding up the main event loop, and so everything freezes until that finishes, and that looks like failure. So this is a much more resilient programming model. So the security of an actor system depends on the control of private addresses. So there are exactly 3 ways that you can obtain the private address of an actor. If there's any other way to get an address, then you do not have a secure system. So first, by creation, when an actor creates a new actor, it receives the new actor's private address. It wouldn't make sense otherwise. So if you make a new actor, you find out how to send messages to it. By construction, an actor can be endowed with private addresses when it is created. And by introduction, an actor can receive messages containing private addresses. This is the most important one, and I'll show you examples of all 3. So I created a language called Neo, which is JavaScript with every bad part removed. Now, reasonable people can disagree on what the bad parts are, but once again, I'm right. So Neo is the language that JavaScript should have been. Never will be, and Neo provides so little new value that there's no reason for us to try to convert to it, just like CoffeeScript or any of those other toys. But it exists. I actually finished this one, and the implementation is in this book. So with Misty, I started with Neo and added actors. And that, I think, becomes a worthwhile language. So Misty is Neo plus actors. The biggest new addition is the send statement, where you have an object which contains a private address, and you will send a message object to it. And there's a special form where you can give a callback, which means if the receiver of your message wants to reply, they can send a message to the message that they received, and your callback will get called. In Misty, it's possible to register a receiver function which will receive all incoming messages, very similar to adding an event listener. You can register a portal function which we use to bootstrap networks. I'll show an example of that in a minute. So it's a cleaner, more modular programming model. It provides automatic connection management, so you don't need to be aware of how the network is configured or anything. Everything just works. It also provides effective failure management, which is really important. We'll talk about that later too. So time for a picture. So this is an actor. It's just a circle, and this one is a worker, It's a very powerful actor. It can do a lot of stuff, and it's potentially dangerous because it has so much power. So it doesn't want to talk directly to the world because it might get confused or corrupted, and that would be bad. So it creates an agent actor. And because a white arrow means you have the address, you can send a message to that thing. So it makes an agent, and it gives the agent its own address. So the agent is going to be able to represent it. Okay, we have a client that's sitting in another machine, and it has an address to the agent. It does not have an address to the worker, so it can't send a message to the worker. So it sends a message to the agent asking, please hook me up to the worker, because I have some things I want the worker to do for me. But the agent doesn't do that. The agent instead creates a liaison actor, which will also have the address of the worker. And the agent will then send a message to the client, and that message contains the address of the liaison. So this is an introduction. As a result of delivering that message, the client now has the address of the liaison and will be able to send it a message. But this particular client doesn't actually want to get its hands dirty talking to anything. So it creates a minion, and it gives that minion the address of the liaison. So now the minion can send a request to the liaison, and the liaison can look at that message and decide, is this something that I want to forward to the worker? And so it can do something that we call attenuation. The worker is very powerful. We don't want to expose that whole power to the web or to the net. So the liaison can decide, is this allowed, is that allowed, and can filter the messages accordingly, so that the worker doesn't have to. All the worker has to do is fulfill the messages. And so if the liaison decides the message is okay, it will send it through. Everybody with me so far? So this is a different way to think about how you organize the work, but it makes sense. In fact, we can look at the way organizations work and create parallel structures very easily in software. So we could have another minion on another machine which also has access to the liaison and could also send messages, and they'll all get funneled through the liaison and sent to the worker. But there's a potential problem in that the liaison cannot determine which came from which minion, and it might be each minion might need to have different restrictions put on what it's allowed to do. And there's an easy solution to that. We just make more actors. So each minion gets its own liaison, and each liaison can have its own policies that it will enforce. It also allows us to have revocation. So the actor can decide to stop either of the liaisons for whatever reasons the agent might have, and so that gives us a way to revoke addresses if we need to. So let's rewind a little bit. So remember this picture I showed you earlier where the client had the address of the agent. How did the client know that? How did he find that out? So I left out some steps, so let's go back and fill that in. So the agent wants to make the worker available to things on the outside. And so it creates a portal, and the portal is going to be used to bootstrap relationships in the actor world. So the portal will have a public address. It'll have the address of the machine. It could be an IP address, or it could even be a domain name. And the client has that. And the client also has the portal's public key. And so the public key is public information, so it's possible to get it. You could get it from Google, or it might be in the contract that gives you access to the services. There are lots of ways you can distribute public keys. So the client encodes its own public key in the portal's public key in order to do a handshake. So in one round trip, the portal can authenticate the client and decide, yeah, you're okay. I'm going to connect you to the agent now. So looking at the worker might have sub-workers of its own doing specialized pieces of the work so that you don't have to do all of the work in one actor. You can have lots of little actors all doing piecework. And you can string them together like subroutines, where you call one and get a partial result back, and you call the next one and you get some stuff back, and you call the last one and you get back. And that's sort of the way we think about networking now, sort of a remote procedure call. We've got a subroutine on the other side of the network, and we call it and get stuff back. But we can order the flow of work in different ways. For example, we could string them all together so that we send a message from one and it sends a message to the next and so on down the line. And then we send the responses back up the line. And this could be a performance benefit if the three sub-workers are on a different machine than the big worker, because we're doing more local communication, and local communication is generally cheaper. Although we have another option, we can bypass those on the return and send the final value directly to the requester. So we can eliminate those middle hops, which we don't need. And so that gets the result back faster, and it also reduces the network loading on the two nodes in the middle. So message passing looks like it might be more expensive than shared memory or other things, but it could actually be significantly faster, particularly if you look at systems where you can do things in parallel. We've got 3 different machines, and they all are going to do something, and so we just send messages to all of them immediately, and so they're all working simultaneously. And there's nothing faster than doing many things at once. So one difficulty you have in distributed systems like this is you're assuming that everything is going to work all the time, and in reality, things don't always work all the time. So we have a model called death before confusion. If a worker gets confused for any reason, it will stop, and it will inform the workers that are dependent on it that it has stopped, and they may decide to also stop. This was a brilliant idea that we got from Erlang. We want our systems to be very reliable, and so we do awful things like exception handling to try to keep everything going all the time. But it's really hard to reason about the correct performance of something which is in a confused state. And so it's unlikely that we're going to think everything through, and in fact, a lot of security problems happen there. Whereas Erlang's approach is, if something gets confused, let's just shut that subsystem down and start over. Because the time when it's easiest to reason about what a program's doing is when it starts. It's, you turn it off and on, and that corrects a lot of problems. And so we automate that in software. So the actors are going to communicate across different machines using the actor protocol. On a network, an actor should not care what language the other actor is written in, as long as it can do the protocol. So we need an actor protocol based on the SAFE protocol to replace HTTPS in actor systems. And we need a JSON-like format that adds blobs and private addresses to the data types that already exist in JSON. JSON, it turns out, is really good for doing distributed systems because it deals really effectively with the update problem. If you have 2 pieces of software that are written in fragile languages, if one is working at one revision level and the other is at a different one, they may fail because fields are not where they expect them to be, and the communication doesn't work. But JSON is so light and flexible that most of those problems are avoided. So strictly speaking, a new programming language is not needed to enjoy the new paradigm. but a new programming language will make it easier to think effectively in the new paradigm, and I think that's really important. And so that's why we need Misty or a language that's inspired by Misty to take the next step. So Misty is a transitional language in which actors are made of functions. And functions are a good thing to build with because functions are wonderful and powerful and great, particularly as they're implemented in languages like JavaScript. After Misty, the next step forward is actors all the way down. In fact, this was the original concept for the actor system, that we get rid of objects, we get rid of functions, we get rid of data structures, we get rid of everything. It's all objects, or it's all actors from this point out. I think that's too big a step. I don't think the mainstream could do that in one leap. So Misty is the first step. So that's the Misty system. If you would like to read more about it, you can find these addresses on the net. Well, this is embarrassing. I don't have a wow finish. Usually I'm able to sum it up and say, yeah, and then so I'm just going to say, yay.